Jai Hind. Today's topic for discussion is CPU scheduling, and this topic is covered under Unit 3 of the subject Operating System. First, we will discuss what is a CPU scheduler. So, what is the meaning of a CPU scheduler? It is a program that is running in the dispatcher, and it is responsible for selecting the next running process, that is which process to be run next. It selects from among the processes in memory that are ready to execute, that is in the ready queue the processes are there which needs to be executed by the processor. Then this algorithm, that is your CPU scheduler, it take this decision. Basically, when the CPU scheduling happen, that is when we have to make a decision that next process to be selected. There are 4 cases. Number 1, a process switches from the running state to waiting state. For example, a process is running, but now some input output activity is required, then it will automatically go from running to waiting state. So now CPU is sitting idle, it has to make a decision. Second case is a process switches from the running to the ready state. That is, for example, you have allotted some time limit to a process and its time limit has been expired, but still its execution left. Then in that case, it will move from running to ready. Then a process switches from waiting state to ready state. That is its input output activity has been completed. Now it want to move back to the ready queue. Then we need to make a decision. For instance, if when it is coming to the ready queue, it is a high priority process, then it need to be executed first. And the last case is a process terminate. That is, a process terminate. Now again CPU has to make a decision which to execute. So these are the 4 cases under which the CPU scheduler makes the decision. Out of these 4, the first and the last one, it corresponds to non-preemptive algorithm, whereas in the case of second and third, it corresponds to preemptive algorithm. So what is the meaning of non-preemptive and preemptive algorithm here? The meaning of preemption, it says taking something, some resource forcibly back from the process. So here what is the resource? Processor is the resource in this case. So what the preemption or the preemptive algorithm says, they are those set of the algorithms whose behavior is such that already running process has to leave the processor, whether it is willing to leave or not. Whereas in the case of the non-preemption, what is happening, that once you have allocated the processor to the your process, then in that case the process will leave the processor only when there is requirement on its behalf and not the requirement by the OS. So 1 and 4, it comes under the category of non-preemptive, and your second and third, it comes under preemptive category. Now once we are discussing about the types of algorithms, CPU scheduling algorithm, then there are certain performance criteria on the basis of which we have to make a decision that which algo is going to be the best. So these are the 5 metrics on the basis of which we make this decision. The first one is CPU utilization. That is, it talk about the percentage of the time that CPU is busy. That is, your algorithm should be such that your CPU should not sit idle. Throughput, the number of processes completed per unit time. That is, the throughput should be maximum. That is, more number of processes should be completed per unit time. In the case of turnaround time, what is turnaround time? That is, once you have submitted a job and it is right from that point to the termination of that job or process, that total time is known by the name turnaround time. So what is its definition? The interval from the time of submission of a process to the time of completion. Waiting time, that is, it is a sum of the periods spent waiting in the ready queue. That is how much time, total time the process has spent in ready queue. So this corresponds to your wait time. And what is the response time? It says that once you have submitted a process, from that point to the first response is being generated by the process, that total duration corresponds to response time. So the time of submission to the time the first response is produced. So when we are talking about the goal of CPU scheduling algorithms, our main aim is to maximize the CPU utilization, throughput, whereas to minimize the turnaround time, wait time and response time. So we need to maximize CPU utilization, throughput and fairness. Fairness is other criteria and you cannot measure it. It says that each and every process should get a chance to be executed. So minimize, and whereas with the in the case of the turnaround time, waiting time and response time, we have to minimize it. These are the scheduling policies which we need to discuss today. The first one is FIFO, first in first out, then round robin, SJF, that is a shortest job first algorithm. What is FIFO? It assigns the CPU based on the order of request. Non-preemptive, it is a process which keeps running on a CPU until it is blocked or terminated. It is also known by the name FCPS, that is first come or the first serve algorithm. Advantage is it is very simple to implement. Disadvantage, that it is having a convoy effect. I will explain the convoy effect with the example too. For a time being, all the processes, they are waiting, all the short processes basically, they are waiting for the one big process to get off the CPU. CPU utilization may be low in this case. Consider a CPU bound process running with many input output bound process. It is in favor of long processes and may not be fair to those short ones. That is, if a 1 minute job is behind a 10-hour job, then in that case, first this got the chance to be executed by the schedule by your CPU processor, and here this job keep on waiting for 10 hours, although it require only 1 minute to get completed. It is troublesome for the time sharing system where each user needs to get a share of the CPU at regular intervals. So let's discuss the FIFO algorithm with the help of this example. Here we are having a set of 4 processes. Their arrival time is given, that is arrival time, that is it is the time when a process first time enter the ready queue. So the process 1 it is 0, for 2 it is 1, 2 and 3 for process number 4. This is the service time. In some places it is also known by the name CPU burst time. So FCPS, if I talk about my ready queue, first we will make a ready queue. So according to this arrival time, the first process which is coming into the ready queue is 1, 2, 3 and 4. That when we draw the Gantt chart, this is the Gantt chart, it is the pictorial representation of the process behavior in the system, that is at what time the processes they are coming or in the system and when they are going from the your processor, when the processor is leaving its execution. So in the case of the FCPS, the first process which need to be executed is process P1 and its execution start at time 0 and its total burst time is 8. So it will consume 8 CPU cycles. After that P2 get a chance, P2 needs burst time 4, that is it will consume next 4 CPU cycles, and when the processor leave it, the time is going to be 12. Then after it P3, according now the one from the ready queue, 1 has finished, 2 is finished. Now come on process 3, its service time is 9. So when the processor leave it, the time is going to be 21, and the last process is 4, that is whose CPU burst time is 5. So when it leave the system, the burst your finish time is going to be 26. So this is the Gantt chart according to the FIFO or FCPS algorithm. Now we are going to compute the waiting time. How we are going to compute the waiting time? For the process P1, its arrival time is 0. And when we have allocated the CPU at time 0. So how much time it has waited? It is 0. That is 0 minus 0. When we go to the process 2, we have allocated the processor to process 2 at time 8. Its arrival time is 1 in the ready queue. So how much time it is spent in the ready queue? It is 8 minus 1. Similarly, for the process, it is going to be 12 minus 2. For process P4, it is going to be 21 minus 3. So the total waiting time comes out to be the summation of all these, and the average you will compute by dividing it by total number of processes, that is 4 in this case. So the average waiting time in this case comes out to be 15.25. Now the next algorithm which we are going to discuss is the SJF algorithm, that is shortest job first algorithm. It is also known by the name STCF, that is shortest time to completion first. Basically, it works on the CPU burst time of all the processes. The process which is having the shortest CPU burst time, it will get a chance to be executed first. What are the advantages? It is optimal in terms of turnaround time. It is very good in terms of short jobs. A small degradation for long jobs in this case. There is another variation of the SJF. This is SJF. SJF basically divided into two: preemptive and non-preemptive. Non-preemptive is known as it is, whereas in the case of the preemptive, it is known by the name SRTF, that is shortest remaining time first algorithm. In the case of the FCPS, we are having only one variant, that is your non-preemptive FCPS. No preemptive version of FCPS is available. Whereas in the case of the SJF, we are having two variants of SJF. One is preemptive and another one is non-preemptive. Non-preemptive is known as it is, whereas in the case of the preemptive, it is known by the name SRTF. So SRTF, it is a preemptive version of SJF. If a job arrives with a shorter time to completion, then in that case, SRTF preempts the CPU for the new job. Also known as SRTCF, that is shortest remaining time to completion first, and it is generally used as a base for comparison. Why we are using SJF and SRTF basically for the comparison? Because it is very difficult to know in advance how much exact time is needed by the process to get that is a CPU burst time. That is very difficult to calculate in advance when the process is starting to execute. So due to this, these algorithms, they are basically being used for the comparison purposes. What are the drawbacks of SJF? Starvation is possible. That is your short jobs, they keep coming in the memory, that is in the ready queue, whereas long jobs, they are never getting the time, CPU time. So it leads to the starvation of the longer ones. There is no way to know the completion time of jobs. This is another drawback. So what is the solution for this? Ask the user who may not know any better. So this is not a better solution. If a user cheats, then the job is killed. So automatically we cannot go for this kind of solution in an interactive system. Let's discuss the SJF with the help of examples. So first we are going to discuss the non-preemptive SJF. These are, again, we are having 4 sets of processes. These are the arrival time and this is the CPU burst time for these 4 processes. So what is happening? We are starting with at time 0. So at time 0 in the ready queue, only one process is there, that is P1, because these are arriving at time 2, 4 and 5. Since in the ready queue only one process is there, so your scheduler, it can't make any decision. So it will execute this very first process. So in this case, P1 got the processor. Since it is a non-preemptive version, so it will take 7 CPU cycles, which is its burst time in this case. Now, when it leave the system, at that time, my system clock is 7 and P4 is the last process to enter in the ready queue at time 5. So, at this particular time, my ready queue picture is such that 2, 4, 2, 3 and then 4. This is the picture, 2, 3 and 4. Now we have to make a decision. CPU burst time minimum we have to take. So in this case, it is 1 corresponding to P3. So the next process is P3. Its burst time is 1. So it will leave the system at 8. Now your P3 is out. So we are having only 2 processes, 2 and 4. Now its CPU burst time is same, 4 and 4. So there is a tie in this case. Whenever tie happen in the system, then in such cases we will resort to FCPS. So here out of 2 and 4, which one is first? P2 process is first. So in this case, P2 will get the chance first. So it will execute after 4, that is after 12 CPU cycles, it will leave the system and now only one process is left. So P4 will get the chance. So this is the Gantt chart for SJF non-preemptive algorithm. How we are going to calculate the waiting time? In the case of P1, its arrival time is 0 and if you look at the Gantt chart, it has been allocated the processor, so no waiting time in this case. In the case of P2, the arrival time is 2 and when it has been given the processor at time 8. So how much time it is spent in the ready queue? It is 8 minus 2. For P3, arrival time is 4 and it get the processor at 7. So how much time it spent in the ready queue? It is 4. 7 minus 4, that is 3. In the case of P4, allocated processor allocation is done at 12. Arrival time is 5. So 12 minus 5, that is 7. So for the average, calculate, do the summation, divide by the total number of processes, and in this case the total number of processes is 4. So when you solve this, its average waiting time comes out to be 4. Now the next case is preemptive SJF. Same numerical, but instead of going for the non-preemptive version, we are going for the preemptive version. So first ready queue, only one process at time 0, that is P1. So we will allocate the processor first to P1. But now what is happening? When it is running, P1 is running, P2 enters. At what time? At time 2 unit. So at time 2 unit, your preemptive SJF algorithm will make a decision. That is, its burst time is 4, and at this time the remaining time is 5. So, which is shorter? P2 is shorter because its burst time is 4, it requires only 4 cycles, whereas in the case of the P1, remaining time is 5. So, what we are doing? We are preempting the resource from the P1 and allocating the resource to P2. So, at time 2, P2 will get a chance to get executed. But at 4, what is happening? A new process is coming in the ready queue, that is your P3. So, P1 is there, then we are having P2, and after it P3 has entered. At unit 4, its requirement is 1. Remaining time for this process, P2 process, is 2. Which is shorter? P3 process is shorter, so it will get the chance to be executed. Now its burst time is 1. P4 is coming at 5, but here P3 is also terminating from the system. So, what is happening here? At time P5, P3 is leaving the system, but a new process is coming in the system. So, now at 5 unit, what is happening? This is the picture of our ready queue. There is P1, P2, P3 is not there, and P4 is there. We need to make a decision. Its remaining time is 5. Its requirement is 2. Its requirement is 4. Which is minimum? P2 requirement is minimum. So, P2 will get a chance. Now, when it is executing, no other process is entering in the ready queue. So, it will finish its execution at 7 unit. Now, we need to make another decision out of P4 and P1. P1 remaining time is 5. P4 requirement is 4. P4 requirement is shorter. So, it will get the processor and it will terminate the system at unit 11. After this, no other processes other than P1 is there in the ready queue. So, P1 will get a chance, and when it comes out from the system, my time is going to be 16. So, this is the Gantt chart for SJF preemptive algorithm. Now, we will compute the waiting time in this case. So, what in the case of P1, when P1 firstly came in the ready queue at 0, it got the scheduler. So, in this case, waiting time is 0 minus 0. But if you look at the Gantt chart, it has reappeared here. So, this implies this is the duration it has spent in the ready queue. So, how you will compute it? You will compute it, that is, at this time it is again been allocated, but at what time? It has left previously at 2, that is 11 minus 2. So, now in this case, the waiting time for P1, it comes out to be 9. Now, compute the waiting time for process P2. So, P2 arrival time is 2. First time when it is allocated the processor, it is again 2. So, no waiting has been done at this point, but P2 again appear here. So, so this is the time it has spent in the ready queue. So, this is 5 minus 4. So, in this case, it is 1. Now, come for P3. P3 arrival time is 4, given the processor at 4. So, in case of P3, it is 4 minus 4, that is 0. Now, come for P4. P4 is coming 5, being allocated the processor at 7. So, in this case, the waiting time is going to be 7 minus 5, that is 2. So, when you compute the average, it comes out to be 3. The next algorithm is your round robin algorithm. It is basically your FCPS with preemption. Now, what is the criteria of preemption in this case? The criteria of preemption in this case is time slice. So, what the round robin says, periodically releases the CPU from long running jobs based on timer interrupts. So, short jobs can get a fair share of CPU time. It is preemptive in nature, that a process can be forced to leave its running state and replaced by another running process. And how the preemption has been enforced? It has been enforced with the help of a parameter, that is time slice, also known by the name time quantum. That is the interval between the timer interrupts. So how the round robin works? So we are saying round robin is FCPS basically, but preemption is there. And what's the policy of the preemption? That is, every process is being allocated certain time quantum value. When that time quantum value got expired, the process need to leave the processor, and the next process is being picked up from the ready queue. So first we need to maintain the ready queue. So in this case, ready queue is like this: P1, P2, P3, and then P4, according to our arrival time. So which process got the processor first? P1, but for how much time? Only for 4 unit. In this case, the time quantum or the time slice is 4 unit. No priority based preemption is being done here. On the time basis, we are doing the preemption. So for 4 unit, P1 will get the processor. Next process in the ready queue is P2. Again for the next 4 cycles, so its remaining time is 4. It's when it will consume all the whole your time slice value. So in this case, it will, when it finish its execution, it will remove from the ready queue. The next is P3, again for 4 unit. So its remaining time is going to be 5 for the next cycle. Your process P4, again the next process is P4, and and for the next cycle, its value is going to be, requirement is going to be 1. Now after first cycle, this is my first cycle, again we will repeat the process. Again we will pick up the processes from the ready queue in the FCPS manner. Again we will allocate the same time quantum value to these processes, but the thing is that now we are taking the things that is the remaining time of these processes. P2 has left the ready queue. So then in the next cycle, P1 will get the time slot for 4 unit. So it will consume its all 4 unit. So P1 again terminated from the, it has left the ready queue. Next process is my P3 from the ready queue. I will pick up the next process. It is P3. Now it will consume only 4 unit. So in this case, the remaining time is 1. Next process is P4. Now in this case, we will allocate the whole value, that is a times 4 unit to the process P4, but its requirement is only 1. So it will consume only 1 cycle, and after that the decision for another process would be made. So it will leave the system at 25, taking only the value into consideration 1. After that P3 again in the next cycle. This is my second cycle finished here. Now I will again repeat the things. In the next cycle, only 1 process is there, P3, its requirement is 1. So it will consume only 1 unit. So now the waiting time in this case is for the P1 coming at 0, given the system at 0, so 0 minus 0, but it is again appearing at 16, left at 4. So this is 16 minus 4. This is its waiting time. For the P2 first we have allocated at 4, its arrival time is 1. So 4 minus 1, P2, it is never appearing again. So this is the waiting time for P2. For P3, this is 8 minus 2, again appearing here, left the system at 12. So this is the waiting time in this slot. So it is your 20 minus 12 again here, and this is your 25 minus 24. For the P4 first allocated at 12, came at 3. So 12 minus 3 plus again appeared here, and this is the waiting time for this P4. So it is your 24 minus 16. So when you compute these values, it comes out to be 18.5. What is the, we are saying that round robin is a FIFO algorithm with the preemption. So what's the difference between the two? With zero cost context switch, RR is always better than FIFO. Context switching may affect RR's performance. Shorter time quantum means more context switching. So we should, the time quantum value should be optimal one. Turnaround time also depends on the size of time quantum. In general, what's the policy? 80% of the CPU burst should be shorter than the time quantum value. These are the references used for preparing the material. So in the today's lecture, we have discussed various scheduling algorithms, CPU scheduling algorithms. Basically, we discussed RR, FCFS and SJF with both the variants, SJF preemption and SJF non-preemption. So this is all about for today's lecture. Thank you and Jai Hind.